Welcome back to compiler construction. In today's lecture, we are going to introduce the basic ideas of our data flow analysis framework. So, to introduce our data flow analysis framework, we have to talk about a number of concepts first. So these are theoretical mathematical concepts, but rest assured we won't dig too deep into these concepts. So we're not going to start a theoretical lecture on lattice theory or something, which can get quite complex, but we're going to introduce as much of the theory as we require for implementing and understanding our data flow analysis. So the three parts we're going to talk about today are partial orders, lattices, and operators on these. So when we construct control flow graphs, we know that we have defined control flow graphs in terms of operations, in terms of basic blocks combining a number of operations, and we know that basic blocks always end in a jump or in some incoming control transfer. And we have seen program points already to make it easier for us to perform some liveness analysis on our code. And this liveness analysis was very useful already because using this we could find for each program point in our program the set of variables that may still be used before the next assignment. And we've also seen how they can be found by traversing the control flow graph. So we collect them in sets and we attach these sets to the program points before and after a basic block. And then we could find out how instructions affect the sets attached to neighboring program points. And we found out how to handle the sets at points where several control flows meet, and then how to enable our control flow graph to capture every possible execution of our program, as well as we've also seen some impossible ones, so we're staying on the safe side of our analysis by making an over-approximation. So this was the final result of our last lecture here. So we're analyzing the liveness of variables. So we have managed to determine the liveness of every variable for every program point. And we have also seen that in order to do it, well, in some cases we have to go around our program many times because our initial analysis of variable liveness that started from our last instruction and going backward to this error here was only complete when we completed another round through our loop again here. So from our liveness analysis of our last lecture, we can now deduce a general procedure of how to do this analysis like these. So in general, we associate program points with sets that represent exactly the information we're interested in, like the liveness of variables. After that, we figure out how these sets actually change, and these sets can change either as a function of instructions or as a function of meeting points between control passes. We need to make a safe assumption at an initial point, and then we need to work out the function throughout the complete control flow graph, and then that's important. We cannot stop as soon as we obtain one set of information we are interested in, but we have to repeat this until the sets stop changing, so until we hit a fixed point here. Now, of course, an important question is it guaranteed that these sets will ever stop changing? And the other question we should ask ourselves is, does this analysis we perform actually get better by repeated application? So the first question we have to answer is concerned with convergence. So in other terms, will this scheme we just proposed actually work in all cases? In order to ensure this, some conditions have to hold. So first, we need to have the sets to have a maximum and minimum possible size. And if the changes we make either only add or remove elements, then we are on the safe side, because then we will necessarily reach a point where they stop changing, and then automatically our analysis ends there. Now this is obviously a very useful property, because otherwise our compiler making use of analysis like these might run forever, which is not very useful obviously. So our next question is, how good is the outcome of the analysis? So good means precise in this case. So we call such an analysis precise if it actually manages to reflect all the control flows that our program can or will take, and it should also be able to ensure that it does not represent any of the control flows that the program will not take. So it has to be precise on both sides. It has to include all the control flows which are actually possible in our program, and it has to exclude all of the control flows which are impossible. Unfortunately, a perfectly precise analysis cannot be derived by a computer, because some of the analysis might actually depend on some input values, and if these input values are not known at compile time, then our computer cannot actually derive the complete precise behavior of our program. Nevertheless, it's still very useful to know if we can assess why the quality of our analysis is lost and how much of this quality is actually lost. And in order to do this, we need a bit of mathematical background. And the first bit of mathematical background we need to know is a bit of background about sets and orders on sets. So sets are just collections of items, and the important thing about sets is that there is no item which can occur twice in a set. And some sets have a order relation, which is as either natural or implied. So you have a set of natural numbers, 1, 2, 3, 4, 5, and so on. And so you might have a natural order relation that 1 is less than 2, 2 is less than 3, 3 is less than 4, and so on. Now, this ordering relation, is just written as this sign less than here, and the order on actual natural numbers is defined using axioms and a rule system, the so-called Peano axiom and rule systems here. Now, some order relation which is not really a natural, but just a defined order relation, but we're so used to it that we think of it as natural, are the letters in our alphabet. So when we look up something in a dictionary or something, we know that A comes before B, B comes before C, C comes before D, and so on until we hit the end of our alphabet. So this lexicographical order of characters is just by definition, and this is even still derived from some very ancient order that was used already several thousand years back in the Phoenician alphabet, and it was just extended by some of the characters that were probably not in use back then, and by convenience these characters like A, Ö, and O were just added to the end of the alphabet. So both orders here, our numerical order for natural numbers and our sorting order for letters in the alphabet, are total orders. So that means they put any pair of set elements in relation to each other. So if we have such a relation, we not only know that 1 is less than 2, but we can also deduce that 1 is also less than 4, because 2 is also less than 3, and 3 is also less than 4 here. However, not all sets do have an order relation. For example, the set of complex natural numbers. So for example, is the number 1 actually less than 1i, so the complex unit on the y-axis here? Now that's an interesting question. And some sets actually allow you to pick a consistent order, and when we do this, we write the ordering relation using a special comparison operator, this ordering operator here, to distinguish it from the operators we already know, like less than or equal or a set include. So such a partial order consists of a tuple, and this tuple contains a set of elements we call P, and this partial order relation here. And such a partial order has a number of properties which are important for further analysis. So first, it's reflective. So an element X is always in the partial order with itself in this relation here. The next property a partial order has is antisymmetry. So if X is in relation to Y and Y is in relation to X, then we can imply that both elements must be identical. Now you can actually, for this example, try to just assume that this would be a less than or equal operator. So we know if X is less than Y and Y is also less than or equal than X. so we have the less than or equal relation on both sides here, then we know that the only solution of this inequation would be that both sides must be identical. And finally, as we've already seen, we can have a larger order on the relation here. So we have the property of transitivity. So if x is in relation to y, and in turn y is in relation to z, then we know that x is also in the same relation to z. And for a total order, we must ensure that for every pair of elements x and y, that either x is in relation to y holds, or the other way around, y is in relation to x. And we've seen, for example, the complex numbers don't fulfill this property, so they wouldn't have a total order here. However, when you want a partial order only, not every pair of elements needs to be comparable using this relation. So let's look at a bit of, well, admittedly silly example, but nevertheless it should serve well to illustrate what this relation and partial orders actually mean. So we can partially order food ingredients here. So we have the relation x is in relation to y, and that denotes that whatever on the left hand side, our x, is an ingredient of whatever is on the right hand side, so our y here. So we know that to make bread we need flour, so flour is an ingredient of bread. But also in order to make pasta we need flour, and also in order to make pasta we need eggs. In order to make bread we need yeast. In order to make lasagna we need pasta, and in order to make a sandwich we need bread. Well, that's simple and obvious, but very, very many simple and obvious things have to be stated explicitly for formal analysis actually to work. Now, if we just write up all these relations one after the other, it's not very easy to see how actual elements relate to each other. So it helps a lot to try to visualize these relations, and we do this using so-called Hasse diagrams. So a Hasse diagram is something like we see in the middle of our slide here. And this Hasse diagram then actually represents our example order, and this also makes use of transitivity. So we see that a sandwich requires bread. This was one of the relations we explicitly stated. And to make bread, you need yeast and flour. And on the other hand, if you want to make lasagna, you need pasta, and pasta also needs flour. So we have a common element here in our Hasse diagram. And we'd also need eggs. So here it's implied that yeast goes into making a sandwich using this transitivity over the bread. But there are also pairs here which are not comparable using our ingredient relation, so we don't know anything about the relationship of yeast and pasta, for example. Now, in order to enable better analysis, we need to define some properties on these relations or on our Hasse diagrams. So the first property we're going to define here is the so-called least upper bound, or LUB. So the least upper bound of a pair of elements is the first thing they have in common when going up the order. So in our example here, the least upper bound of yeast and flour would be bread. And also the least upper bound of flour and eggs, in our example here, would be pasta. Now there's another property we need when working with these Hasse diagrams, and this is so-called the greatest lower bound, or GLB. So the greatest lower bound of an element pair is the first thing they have in common when going down the order. So if we look at bread and pasta, and we are going down the order here, we see we have these three elements, and the element they have in common is of course also the first element they have in common. This is flour. If we want to figure out what the greatest lower bound of sandwiches and lasagna is, we also need to go down our Hasse diagram until we hit the first common element here, which obviously would also be flour. And now what's important is that partial orders do not necessarily have a unique top or bottom. So for example, if we have yeast and eggs, we cannot find a greatest lower bound, because for yeast we have to go up here. For eggs, we go up this path here, so we cannot find anything that's in common, that's both using yeast and eggs, so there is no GLB of yeast and eggs. And on the other way around, it would also be difficult to find a lower upper bound for sandwich going up and pasta, because if we go up these relations here, we won't find anything that's in common anymore. So after we defined these properties of the Hasse diagrams, we can now define lattices. So a lattice is a partial order with a special property. So one of the special properties of lattices is that any finite, so any finite non-empty subset has a least upper bound and a greatest lower bound. And a simple example for this are the natural numbers. So the natural numbers ordered by the relation less than form a lattice. So for any finite subset of our natural numbers, we know that the least upper bound is the biggest number in our set of numbers, and the greatest lower bound, in turn, is the smallest number in this set. For our natural numbers, we know that we have a unique bottom element, and we indicate it like this, with this t turned on its head, and that's the number 0. Well, in case you include the number 0 in your natural numbers. But natural numbers do not have a unique top element, which we indicate with this regular t-shaped character here, since they are countably infinite many natural numbers. And you can also pick infinite subsets of natural numbers, for example, a subset that consists only of even numbers, of prime numbers, of all the numbers that are larger than 42, and so on. Now, if we have defined a lattice, we can now also define a so-called complete lattice. So a lattice is called complete if any non-empty subset of that lattice has a least upper bound and a greatest lower bound. So these complete lattices then have top elements, so the so-called biggest element, as well as bottom, so-called smallest element. So for a complete lattice L with a relation, then we have the top element is the least upper bound of our elements in the lattice, and the greatest lower bound here, the smallest element here is the greatest lower bound of our lattice here. And every finite lattice, so a lattice with a finite number of elements, is complete. And we're just stating this, so we're not proving this. If you're interested in proofs about this, let us know. We can provide you with additional information on lattices. Now, in order to have symbols that are actually independent of how we choose the order in our lattice, we are going to define two operators. So we'll define the meet operator, which is written with this symbol here, x meet y, and this is just by definition the greatest lower bound of our two elements x and y. And we also have the join operator using this symbol here, so x join y is the least upper bound of x and y. And using these, we can now naturally extend these to sets of more elements. So we can say x meet y meet z, and this is the greatest lower bound of the greatest lower bound of x and y, and this is combined in this outer greatest lower bound with z. So we can also define power sets. So let's just consider a set consisting of the elements a, b, and c. So we can now define the Cartesian product of this set, and this is the Cartesian product with itself, so it's just a set of all pairs. So it's AB, AC, and BC. So just combining one element of the set with all the others. And since these are sets, we don't care about the order, so BA would be the same as AB, so we only count it once here. And now the power set of our set here is actually the combination of actually 0 to more of the elements of our set. So the power set would include the empty set, it would include all of our three elements as a single set element, then it would contain all the elements of a Cartesian product, and the power set would also include the combination of all three of our elements in the set. So the power set really contains all the sets that are possible combinations of our elements in our basic set here, including the empty set where none of these elements is present. And our power set gives a partial order by the subset relation, which is a subset include or equal operator. So based on this, we can now define the power set lattice here. So our ordering relation would be the set include operator here. Our meet operation is just the meet operator or cut operator between different sets, and our join operator is the join operator between sets, or our set unification operator. So now we can draw our Hasse diagram related to our power sets here. So our top element is the element including all of the elements of our sets here. Our bottom element is just the empty set, always described using this circle with a slash through it. And then we can actually have this include relation. So we know that the set AB is a partial set of ABC. We know that AC is a partial set of ABC, and in turn BC is also a partial set of ABC. And then we have a bit of more complex relations, because in the next level we only have our sets with single elements from our power set here. So just the set containing the element A, the set containing the element B, and the set containing the element C. So A is part of AB and AC, B in turn is part of AB and BC, and finally C is part of the sets AC and BC as well. And the final relation we have in our power set lattice here is this relation of the empty set. So the empty set is part of every set. So essentially, we can also include these three relations here at the bottom. Now, the funny thing is that if you just switch the ordering relation and the operators, well, you can just turn your whole Hasse diagram upside down. So if you switch the ordering relation around and also the meet and join operator around, and then you have the empty set at the top, you have the complete set of all of the three elements at the bottom here, and you can go through this diagram and you see this also works with supersets instead of subsets, and then you just need to switch over your operators here. Now this was all just a bit of mathematical theory, and the question we have to ask ourselves is, how can we actually make use of this? Now, the example we considered so far is the analysis of live variables. So let's just consider our three element set ABC would be three variables that are part of a short program. So if we use this set as the three variables of a short program, then every possible choice of live variables corresponds to a point in our power set lattice here. Now, if we can express the effect of statements as a transfer function from one place to another in the lattice, so only following the legal transitions in our lattice, so everywhere we drew a line connecting elements, then we can argue that the set attached to a program point only moves in one direction with regard to the order when it's applied repeatedly. So essentially what we do is we map these sets of variables to such a Hasse diagram in our lattice here, and then we can figure out if our changes we apply to the sets of variables are actually compatible with the lattice order we defined. And this means it will either end up at the top or it will stop somewhere before the top. So using this, we can combine our program point analysis we've seen so far with our lattice theory using what we call transfer functions. So such a transfer function is simply a formalization of the idea that the instruction, that is the instruction between two program points in our program, is a function that transforms state from one place in the lattice to another. So for a given instruction I, for our forward analysis, we know that the outset of I is the inset of I on which we apply our transfer function f. And on the other way around, for a backward analysis, and that's what we've seen so far in our liveness analysis, we know that the inset of an instruction I is applying the function f to the outset of that instruction I. And if we defined it for single instructions, in turn, we can now define it for basic blocks here. So the function of a basic block B is simply the nesting of the functions of all the component instructions I1 to IN of our basic block B. So if we have a basic block B here, we just split it up into its single instructions, and then we can consider for our forward analysis what happens when we go down our list of instructions in our basic block. So first we apply F1 to what comes afterwards, so this is F2, and then F3 until we have the last instruction here. So this would work that way here to define the outset given an inset, and we can do it the other way around using a backward analysis. So essentially having the outset as an input here and then going upwards, going back again through all of our functions that represent the changes to state introduced by that single instruction in the given order. Now this gets more interesting and useful where control paths meet. So for points where multiple control flows intersect, then we can finally use our meet and join operators here. So the inset of a basic block where control flows meet is the meet operator of the outset of all of our predecessors of our basic block, and we call these predecessors just B prime, which can be one or more. And if you do an backward analysis, then we have to go in the other direction again. So the outset of a basic block B is just the join of all the possible insets of all the successors of B. Now, if we really wanted to, we could use actually this join operator instead and reverse the orders. So with a meet operator, transfers and the lattice move towards its bottom here, whereas with our join operator, transfers and our lattice would move towards the top. Now, this may seem all very constructed and unnatural to you, so I thought I'd show you also that Hasse diagrams can be used for other applications, so not involving any sandwiches or bread or something, but we'll include an example from hardware modeling here. So if you know a bit about electronics, you know that there are not only states 0 and 1 for digital electronics. That's just what we make you believe in computer science sometimes, unfortunately. But in a sense, in real electronics, of course, everything is analog, so you can have intermediate levels. So accordingly, when you want to describe real hardware, for example, in a hardware description language such as VHDL, you need to be able to define the strengths of signals. So when two signals meet and these signals have different logical polarity, you need to figure out which actual signal level comes out as a combination of these two. So if you did a bit of electronics, you may know about pull-up resistors or pull-down resistors, something like this. And this is exactly what this is related to. So you should be able to model these components such as a pull-up or effects such as a line with a state that has high impedance. And so for electronic circuits, we define a Hasse diagram like this. So we have an undefined signal, which we call X, and this is ordered above our defined signals, which are the logical levels 0 and 1. Then we have a weak undefined strength of signal, which then again is above our low and high, which are not logical levels again, but we're getting analog here. Then we have another so-called pre-charge level. So if there's already a charge online, we can still define this. And finally, we have high impedance. So whenever there's a signal combining, for example, a 0 and a high impedance signal, then the 0 always wins because the 0 has a relation that's above the Z in our diagram here. But of course, if we have a direct clash of logical levels of the same strength, so if we have a 0 and a 1, then you can't compare these. And in real life, you have a short circuit. You might even destroy your circuit using this. And this is a typical example for such an application here. So you might have a bus carrying a common bit signal here. This bus has some capacity, so there's some charge on the line that might try to influence your signal here. And so essentially what you might have here is a function defining the switching behavior of your lower FET transistor here. And you have maybe a clock defining the functionality of your upper transistor. So your upper transistor transmits to your supply voltage, whereas your lower transistor connects to ground here. And so it's interesting, of course, to see what happens if both transistors are switched on at the same time. And in order to model this, you can apply Hasse diagrams also like this. So they're useful outside of compiler analysis too. So after we did this rather formal introduction to lattices and orders and sets and so on, we'll get a bit more back to the practical side in our next lecture. So in our next lecture, we'll continue with our data flow analysis, which are part of our optimization framework. So that's all for today. Thanks for listening, and until next time, bye.